All right, so now that we have this pulled up on our whiteboard, we've set up our method, let's go ahead and start solving this. The first thing I want to do is find these relationships. So these relationships are pretty easy to find in the inside cover of your book. You'll find the fundamental equations of dynamics. We know that we're dealing with particle curvilinear motion, right? We're moving along a curved line here. Over here on this side, we have x, y, and z. We have r, theta, and z, right? This is our cylindrical components that we're going to use. We also have n, t, b. Those are our normal and tangential components. So in this case, we're going to be using this set here. So I just took a little screenshot of that, so we have that available. But I do want to start here by figuring out our theta dot, and our theta double dot. So let's start with that. Let's first start with our r. Now we said r was 0.1 t to the third power. R dot is going to be the derivative of that. So since this is a derivative with respect to time, remember that we're doing this with respect to time, this is just going to be 0.3 times t squared. Taking the second derivative is going to be 0.6 times t. That's our first set of values. Let's do theta as well. Theta is going to be 4 times t to the 3/2 power. So our first derivative is going to be 3/2 times that, which will be 6 times t to the 1/2 power. We take that derivative, make that dot a little bit bigger, take the second derivative with respect to time. Remember that this is also, we could also think about this as omega and alpha here. Take that second derivative here, we take that half, this is going to be 3, and we have t to the negative 1/2 power. So there are our values. Let's go ahead and evaluate this at our time. We want to find this at our time t, so r of 1.5 seconds, plugging that in, that'll be 0.1 times t to the third power. So I'm going to get out my calculator here. 0.1 times 1.5 to the third power. I'm going to get that as 0.3375. I'm going to go ahead and take that to 4 significant figures, since I'm going to be solving, my solution will be in terms of 3 significant figures. That's kind of the default for engineering. Plug this into the r dot formula, or the relationship there. So we have 0.3 times 1.5, so 0.3 times 1.5 squared. Plugging that into my calculator, I will get 0.675. Finding the r double dot, that'll be 0.6 times 1.5. This is very easy math. It'll just be 9. In this case, because it is 9, 0, it'll actually be 0.9. All right. So moving over here, let's talk about theta at 1.5 seconds. That'll be 4 times 1.5 times 3 to the 3/2 power. So 4 times 1.5 to the 3/2 power. We'll go to 3 significant figures here. This will be 7. Sorry, I said 3. I should say 4. 4 significant figures would be 7.348. Theta dot at 1.5 seconds is 6 times 1.5. Take the square root, or to the 1/2 power. That will also be 7.348. And theta double dot is 1.5. When we do this, it'll be 3 divided by, and we can say 3 divided by the square root of 1.5, or 1.5, yep. So take the square root, divide by the square root of 1.5. This will be 2.5 449. Now in this case, we haven't put any units here. Let's take a look at our equations here. Now theta, in most cases, we're going to be talking about this in rads. So we take this first one, we said theta is in rads. So we take the derivative, this will be rads per second. We take this derivative, this will be rads per second squared. So let's put these units in here. Theta is in rads. Theta dot is rads per second. Theta double dot is rads per second squared. Coming over here to R, R is 1.2 in terms of meters. So let's put that in here. Doing that, then our first derivative will be meters per second, and our second derivative will be meters per second squared. So R is in meters, R dot is in meters per second. Make that a little bigger. And then R double dot is meters per second squared. All right, so now we've done the first step, which is find R theta to R double dot theta double dot. We found those values. The next step is to start applying our relationships. So I'm going to move my relationships down here to make my life a little easier. I've got my values here. Now I want to find velocity. So basically, in this case, we're finding velocity. In this case, we are not really concerned about the z direction. This is only a two-dimensional problem. So let's just find VR. Now VR is quite simple. VR is just going to be R dot. R dot's pretty simple to find. That's just going to be 0.675 meters per second. Plugging in R dot up here. The transverse component, this is our radial component. Remember, radial. This will be our transverse component. Our transverse component is R times theta dot. And the way I like to think about this is if this is our transverse component going this way, and this is our radial component going this way, the radius of this will matter. If we have a small radius, it's almost like a moment, right? The longer the moment arm, the longer the r, the greater this velocity is going to be. So if we have a large r, we will have a large theta dot. Oop, I jumped there a little bit. R is going to be 0.3375, and that's meters, times theta dot. Theta dot in this case is 7.348 rads per second. So when I do that multiplication, remember that rads is unitless, right? Rads are rad because they're unitless. So if we do that 0.3375 times 7.348, we'll get our answer of 2.48 meters per second. And there's our velocity. Acceleration can be found much in the same way. We'll plug in our values. So to find our accelerations, right? And these are our two components, right? This is our radial component. This is our transverse component. If we want to find our total, we just combine those. Our total is the sum of squares. I'm not going to bother with that math. I'll let you do that for yourself. Finding our acceleration, very similar. We're going to say, okay, using these relationships right here, we say AR is equal to R double dot minus R times theta dot squared. And I want to be clear that, right, using PEMDAS, we know that theta dot is the only thing squared here, and it'll also make sense with the units when we get to that. We said A theta, or the transverse acceleration, is going to be R theta double dot plus 2R dot times theta dot. And we can plug in these values. So R double dot coming from up here is 0.9 meters per second squared minus our radius. Our radius we found was 0.3375 meters times our theta dot squared. Our theta dot in this case is 7.348 rads per second squared, or sorry, rads per second, and then we're going to square that amount. So if we simplify this, it's going to be 0.9. And over here, we got meters times rads over seconds squared. So our units are going to be, excuse me, rad squared. Remember that rads are unitless, so these drop out. So we just have meters per second squared here. So let's do that. 0.3375 times 7.348 squared. This is going to be minus 18.2, and this is meters per second squared. So when we do that, we're actually going to get a negative number here. 0.9 minus 18.2 gets us a value of negative 17.3 meters per second. And that is our A of R component. That's our radial component of acceleration. A theta is going to be R. In this case, R is given up here. That's 0.3375 times theta dot. Theta dot is 2.449 plus 2 times R dot. R dot is 0.675. Theta dot is 7.348. Let's look at our units here. This is in meters because this is a radius. We've got theta double dot, that's rads per second squared. Over here we've got R dot, which is meters per second, excuse me. And theta dot is our angular acceleration. That's going to be, angular velocity. That's going to be rads per second. So looking at this, since rads are unitless, this gives us meters per second squared here. That also gives us meters times seconds. So that'll be meters per second for both of these. Excellent. And let's erase this. We'll define a little line here. So plugging that in, 3.3375 times 2.449. This gives me a positive value of 8.265 plus 2 times 0.675 times 7.348. That's going to be 9.920. All right, so combining these two components, since they're both positive, will give me a value of 10.7 meters per second squared. That is our transverse component. Transverse component. Over on this other side, we have our radial component. So combining these to get our total, we get the sum of AR squared plus A theta squared. That's going to be our total acceleration. All right, so taking a look at our problem, we were asked to find the magnitude and velocity of acceleration. The first steps are to find the R double dots, and theta dot, theta double dots, which we could also think of as omega and alpha. Once we have those, we find those values, find those derivatives first. We find the values. We could say that's actually kind of part A. Part A is derivatives. Find those derivatives. And part B, let me get in a little closer here. Part A is find the derivatives with respect to time. Part B is evaluate at t equals 1.5 seconds. Once we have those, we plug in our values into our VR and V theta equations to find our transverse and radial components. And then we do the same thing for acceleration using our relationships. And to find the magnitudes, all we need to do is take the sum of squares to find the total acceleration. And in this case, I wrote total acceleration up here. Let's change that to total velocity. So v total equals the sum of squares of vr squared plus v theta squared. And that's how we approach a r theta, or radial polar coordinate cylindrical component problem.